Okay, let's go ahead and start talking about reflection. So with refraction, when a ray of light sees a new material, it simply bends and keeps going. But when the light cannot actually get through to the other material, it bounces off at the opposite of the incident angle. And this is called reflection, when the light bounces backwards. We're going to see the first example of this using Snell's law again. We're just going to write out the equation and take a good look at it at first. So the time before we looked at when the light was coming from air into water and saw the bending or the refraction of the ray. But let's consider a more extreme example where we are in the water. So here we are floating inside the water, looking up at the surface of the water. And if you do this, you will notice that if you look at a steep enough angle, the surface of the water will look like a mirror. You will only see the inside of the lake, the pool, whatever water you're in. You won't actually be able to see outside of the air. You will effectively see a cone where you can look out, and beyond that cone, at steeper angles, you will only see the reflection of the water. So what's going on there? If we look more carefully at Snell's law, so let's take a look at some rays that are coming from the water to the air with the Snell's law. The N1 is always where the ray is starting, and N2 is always where the ray is trying to end up. In this case, N2 is the air. So N1 equals 1.33 in this case, and N2 equals 1. Now let us make the angle really steep for the ray in the water. In fact, let's make it really steep. Let's say that the angle is close to 90 degrees. When the angle is close to 90 degrees, the sine of 90 degrees is 1. So let's make this close to 1, this quantity here. And we know that N1 is 1.33 and N2 is 1. So now we want to find this angle here. What's the angle going to be in the air? Well, let's take this down here. If you take 1.33 times 1 divided by 1, that's just 1.33 on the left side, equals sine of theta 2. Well, this is a bit of a problem because sine of any number cannot go beyond 1 or negative 1. So there is no angle that can possibly make this side equal to 1.33. The angle is imaginary, meaning it doesn't exist in the real world. So we can never actually solve this equation when theta 1 is too large. When this sign on this side of the equation gets too big, you can't solve it. So what does that mean? Well, let me draw a few examples of the ray coming out, and perhaps you will see what's going on. So we make a pretty shallow angle, and in the air it comes out steeply. So we make the water angle a little steeper. Let's change colors so that we don't confuse rays. This is a little steeper, so the output comes a little steeper. And then we get really steep in the water until the light barely escapes into the air at nearly 90 degrees. Once this output ray in the air reaches 90 degrees, that's the limit to what it can do. If you make this input angle any steeper than that, the light will actually be reflected. So this angle here, this blue ray, is so steep that it actually gets reflected in the water at the same, if I could draw a straight line, at the same angle that the ray came in. So this is theta 1 and this is theta 2, and the angles are equal. So let's rewrite Snell's law to figure out when this exactly occurs. You'll get quite used to writing this when you are trying to find out things like this. Right now what we're trying to find out is called the critical angle. That means this is the angle, this is the steepest angle you can make in the water that can still escape into the air. If you make anything steeper, then the light is reflected. And when it reflects in this fashion, when this is a higher index, when into, no, sorry, I got that backwards. This is what you have to be careful about. You always start from where the ray starts. So the ray is starting here and ending here. So when N1 is greater than N2, then once you've gone past the critical angle and you've got reflection, that is what we call total internal reflection. The reason we give this a fancy name is because all of the light is reflected, which is pretty uncommon in optics and light, for all of the light to be reflected, but that is at the critical angle. So to solve that, we use Snell's equation, Snell's law, and we say, okay, theta 2, we're going to make 90 degrees just when the light is able to escape. So N2 sine of 90 equals N1 sine, and this incoming angle is what we've defined as the critical angle, so I'm going to label that theta c. Sine of 90 is just 1, so now we have sine theta c equals, I'm going to divide by N1 on both sides, N2 over N1. And so then you take the inverse sine of both sides, and you have the critical angle for total internal reflection is the inverse sine of N2 over N1, where N1, I'm going to say this again, where N1 is the medium where the ray starts, and N2 is where the ray is trying to exit. It has nothing to do with which medium has a higher index. It's just about where the ray starts. So this right here is the critical angle. And if theta 1, the input angle, is greater than the critical angle, then TIR, that's what we call total internal reflection in optics, happens. And when that happens, reflection occurs. And when we have reflection, the incident angle is equal to the output angle. Well, from this frame of reference, it's actually equal to the opposite of the input angle. So total internal reflection is very, very important. You might think, big deal, it just tells me what cone of an angle I can look out of the water at. But the reason it's very important is because when you try to make a device with light to channel light, let's say that This is a really bad drawing of the United States and Canada, all of North America. Let's say that you live here in Atlanta and you want to communicate with your buddy in San Francisco. Well, we build fiber optic cables to do that, which send the signal from you to your buddy in San Francisco via light. And we have to channel that light so it gets all the way there. The way we do this is we make glass cables where the index in the middle of the channel is higher than the index outside of that channel. So we've got this glass rod here. And we're very careful to make sure that that N1, is greater than N2, so that we can have a critical angle, so that the light will be totally internally reflected as it travels from you to your buddy to make sure the signal gets all the way there. That's just one example of total internal reflection. And total internal reflection is a special case of reflection. The fact that the angles are the same is true in all reflection. But in other cases of reflection, not all light is transmitted, like in TIR. And we will get to that next time. Or probably next time, maybe a few videos after that. We'll see.